Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is lecture video 20, or video 20, and lecture 8, and we are in part 3 of simple regression. Last time we reviewed the least squares regression line from earlier sections, talked about the simple linear regression model, and the derivation of the least squares estimators, and I want to caution you that the derivation of these estimators is done using a different model than many books and calculators, so we have to be careful with that. All right, so the summary is that the derived least square estimator for alpha hat using the model in the book is y bar, and for beta hat, it is the sum of the differences between x and y and their means divided by the sum of squares of xi minus x bar. And so we can rewrite this as the sum of xi yi minus 1 over n sum of xi times the sum of yi. This is the calculation formula that we want to use, the shortcut or calculation formula. And then on the bottom we can rewrite this using some algebra as sum of xi squared minus 1 over n sum of xi quantity squared. Notice the similarities in these two equations, the numerator and the denominator. When x and y are different, but if they were the same, that would be xi squared. And again, x and y are different, but if they were the same, it would be the sum of xi quantity squared. So we have the same pattern going on both in the numerator and the denominator. All right. So our example is that we're going to let y be the compressive strength of some alloy, metal. X is going to be the concentration in percentage of some additive. We want to determine the least squares estimators of alpha and beta, and we need to show all steps. So looking at our equations here, we need the sum of x times y, we need the sum of x, we need the sum of y, and we need the sum of x squared, and here is the sum of x again. So we need those four quantities. And so you can use a table, and you could come over here and say that the sum of x's are 140 here, and the sum of y's are 201.1. And if you wanted to, you could make a line for x squared and y squared, and you can square those numbers and then sum them up. And if you sum up the x squares, you will get 3,500, but you would have to say 25, 100, 225, 400, 625, 900, and I forget what 35 squared is, but I can figure that out pretty quick. So 1225. And then you have to add those up, and this is the sum of xi squared. This is the sum of yi. This is the sum of xi. And then if we did the same thing with the y's, which are a little messier, we would get that the sum of yi squared is 5830.55. This is the sum of yi quantity squared. And then we could do another line for x times y, and we find out that the sum of x times y is 4211. So 140, then 201.1, 3,500, 5830.55. You could also use a calculator to get these. Most calculators that are scientific, they have a place for you to enter the data. Excuse me. And so you can punch in the numbers into a table and then do, in this case, you would do two variable statistics, and it will give you all of these quantities. X bar is, let me find, X bar is 20. So this is going to be 140 divided by n, which is 1, 2, 3, 4, 5, 6, 7. N equals 7. Okay? So we do 140 over 7, we get 20. We have y bar is going to be 201.1 divided by 7, and that gives us 28.72857. And now we're going to do something that's not really the best practice here. Just for convenience of this example, we're going to round this to 28.73. All right? You really, well, I guess we can do this because we're using this as an estimator. We're not using it in any other calculations. So y hat is equal to y bar, which is approximately 28.73 to 2 decimal places. We use one more decimal place than we had in our data. Our data has 1 decimal place, so our calculations, this is a scientific rule, should have 1 more decimal place than the data. So that's why we're rounding to 2 decimal places. Now, S of xy, again, that's equal to the sum of xi, yi, minus 1 over n, sum of xi times the sum of yi. You can use parentheses if you like, or not. I think it's fairly clear that we have this situation. And then we fill in, that's 4211 minus 1 over 7 times sum of x is 140, and sum of y is 201.1. And when we calculate this out, we get exactly 189. Okay? And then the sum of squares of x's are equal to the sum of xi quantity squared minus 1 over n, sum of xi quantity squared. I definitely need my parentheses for this. And so this will be 3,500 minus 1 over 7 times 140 squared. And this gives me 700. Okay. And I'm going to do SYY even though I don't really have to here. So SYY is going to be the sum of yi squared minus 1 over n, sum of yi quantity squared. The sum of yi squared is 5830.55 minus 1 over 7 times 201.1 quantity squared. And this is, using the calculator, 5830.55 minus 201.1 squared divided by 7 gives me 53.234. Okay. Now, beta hat is equal to S of xy divided by S of xx. And using our book's notation, so this is 189 divided by 700. And this is equal to 0.27. Let me check and make sure that that's not a rounded value. If it is, we'll write out the exact. But no, this is exactly the answer. So 0.27 is our estimate for beta hat. So to summarize, we have alpha hat is 28.73, beta hat is 0.27. Okay, so now we have our least squares estimators, and we can use these to write a line. And again, remember that the line that we're going to use is here, so we could say y hat is equal to 28.73 plus 0.27 times x minus, and x bar was, I believe, 20? Yes, 20, minus 20. And we could simplify this. So we could have, this would equal, I'll get rid of the arrow there. So this is going to be 28.73 minus, I'm going to distribute the 0.27 times 20, so 0.27 times 20 plus 28.73. That's going to give me 23.33 plus 0.27x. So that will be my simplified regression line. All right. And so now I'm going to modify this value here as 23.33 and then obtain a new estimate. So I have 23.33 plus 0.27 times 16 gives me 2765. This is my predicted value for x equals 16. Now if I look at my data, 27.8 at 15, 27.65 at 16, those are fairly close values. So, so that tells me that I'm closer. If I want to predict the value at x equals 15, y hat of 15 will equal 23.33 plus 0.27 times 15. So I'll basically subtract 0.27 from the value that I had. So 23.33 plus 0.27 times 15 will be 27.38. Now, y of 16, the actual value, or 15, not 16. We don't have a 16 in the data. Y of 15 was equal to 27.8. So, and we will talk about, what we're going to talk about now are residuals, and that is the difference between these two values, that is, these two values. We can only calculate residuals for values of x that actually show up in our data, okay? But the residuals, these are the observed values of epsilon I. We're going to use little e sub I. And so we take y sub I minus y hat, or yi hat, okay? And so in this case, so y and I have to just count which values these are. 1, 2, 3. So this was the third value, and so the third pair of data. And so I'm going to say y sub 3. So I say y sub 3 minus y3 hat is equal to 27.80 minus 27.38. So this is y and this is y hat. We always take y minus y hat. Some of these are negative and some of these are positive. So this is going to be a positive residual, 27.8 minus 27.38, and that is a 0.42. So this is epsilon 3, the third observation, the observed residual. Okay. Now, the sum of the residuals is the sum of yi minus yi hat. And so if I substitute in for yi hat, the equation that we use is y bar plus beta hat. See, this is alpha hat, right? And then, so I've substituted in y bar there. And so I have this minus sign, so make sure that you use your parentheses here. And then when we simplify this, we'd get yi minus y bar. And we can group these together if we like. Minus beta hat xi minus x bar. Okay. So now we have the summation of this. We can distribute the summation across these two quantities. And we have the sum of yi minus y bar minus beta hat, don't forget the hat, sum of xi minus x bar. Well, the sum of yi minus y bar, that's always 0, because that's the sum of yi minus the sum of y bar. And the sum of y bar equals 1 over n, sum of yi. So the sum of, so this, and I've got that, this is going to equal, I'm sorry, let's not write it like that. The sum of y bar, is equal to n times y bar, which is equal to n times 1 over n, sum of yi. And these cancel, And so it's just equal to the sum of yi. So I'm left with the sum of yi minus the sum of yi, whatever those values are. I'm subtracting something from itself, and that's 0. And the same thing is true with xi minus x bar. The sum of the values minus their mean is always 0. So the sum of these observed residuals is always going to be 0, okay? Because it's a sum of the variation from from the mean, okay, from their mean. Let me clean this up so it's not quite so messy. But please do make sure that you include the hat for beta here. I just, it was there and then it was here and then I just forgot it. So make sure you please include it in your notes. So here is a sketch of the points, okay? So we have this point x sub I, y I hat, and that is going to be on the line. So that's a point on the line. So the line is given by y, y hat, right? And so if we substitute, we have x sub I, and then for yi hat, that's the mean at x sub I. That's mu, the mean of y at x sub I. And so here is the actual observed point. In this case, it's xi, yi. And in this case, we're saying that it's above the line. And so epsilon I would simply be the distance between the observed value of y and the predicted value of y at x sub I. Now, if we chose this point here, it's below. So this would be x sub I, y sub I, and this point would be x sub I, we'll call it prime, x sub I prime. And so we'd say this is x sub I prime, a different value, comma yi. And so, and we can use a prime there for those two. And so epsilon I prime is going to be yi prime minus y, oh, these are hat, there's a hat here. So yi hat prime, okay? And in this case, it's going to be negative because the point is below the line. If the point's above the line, the residual's positive. If the point's below the line, the residual's negative. So let's determine the residuals and fitted values for the data in our example 1 above. Okay? So first we have alpha hat was equal to 28.73. And then we had beta hat is equal to 0.27, and x bar is equal to 20. And we have y hat is equal to alpha hat plus beta hat x minus x bar equals 28.73 plus 0.27 x minus 20. Okay? And yi hat is going to be 28.73 plus 0.27 times xi minus 20. So we're just putting the I in there. And so now I've put in the actual values. And what we need is we need the calculated value, yi hat. We're going to use this equation for each value of x. So we'll plug in 5, and then we'll plug in 10, and then we'll plug in 15, and so forth. And we'll do the calculation and get the actual values. So what I have here is 24.68, and then 26.03, 27.38, 28.73, 30.08, 31.43, and 32.78. And then we're going to take yi minus yi hat. And so this is going to be a negative, or actually 24.70. So this is going to be a positive 0.02. Whoops. Sorry about that. Let's go back to where we were. Oh, it looks like it erased my last bit. So, little error there, 28.73, 0.27, 20, 28.73 plus 0.27 times x minus x bar. Same thing with the I for x27, xi minus x bar. We had these written down, 24.68, 26.03, 27.38, 28.73, 30.08, 31.43, 32.78. This is going to be 0.02, negative 0.83, 0.42, 0.97, 0.02, negative 0.63, and 0.02. All right, and when I add all these up, I get negative 0.01, which is not equal to 0, but this is because of rounding error only. If you have the exact values and don't round these to 2 decimal places, then you will get that this is actually 0. But due to rounding error, we didn't come out exactly that, but it is very, very close to 0, isn't it? Okay. And so again, if you did these calculations precisely, you would always get 0. Okay. It can't help but be that. All right. So again, the only error there is just in our rounding to 2 decimal places instead of 3 or 4 or whatever we needed. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.